let's say there's a car sitting on the road and it has a siren making some noise. Sound is a longitudinal wave, which means that it's nothing more than compressions in the air followed by rarefactions. So here's a compression that's produced by the siren, and those compressed air molecules push on their neighbors, causing the neighbors to become compressed. So the compression travels outward. But the sound continues. So in the time that this one expands out, a new compression takes its place. It's produced by the siren. After a little time, these compressions each travel out, but another compression is formed because the sound continues. After a little more time, these compressions all expand out, but during that time, a new compression was formed by the siren, which keeps on blaring. If you're a person standing here, you hear the noise. But what happens if the car is moving? Well, it sends out a first compression, and after a little time, that compression expands. But during that time, the car traveled forward. So the next compression gets sent out from here. A little bit of time passes. These compressions expand out, but during that time, the car travels forward. So the next compression is sent out from here. If we let more time pass, these all expand out, but during that time, the car travels forward. So the next compression is sent from here. So we see that if you're standing in front of the vehicle, these wavefronts that I've highlighted in purple now have a smaller wavelength. The compressions are closer together. So we have a lower wavelength and therefore a higher frequency. And a higher frequency means the pitch sounds higher. On the other hand, if you're standing behind the car, then these wavefronts, which come forward and strike you, are much farther apart. They have a much longer or higher wavelength, and a much lower frequency as a result. These crests are far less frequent. We can produce the same effect by having the person run toward the car. So here she is down here, and she's running in, and because she's running toward the car, she intercepts or strikes these wavefronts more frequently. The equation for the Doppler effect is this. F0 is the frequency that is actually emitted by the car. It's the frequency you would hear if the car was stationary and if the person were stationary. F prime is the frequency that the person actually hears. C is the speed of the waves, so how fast does sound travel? How fast do these compressions travel through the air? And we see that the equation depends on the observed frequency that the person hears, depends on both how fast she is going, her speed or velocity, and also how fast the source of the waves is traveling. We often take this and just write it as VO, and down here this is just VS. These are actually velocities, and so there's a slight convention here. We say that any velocity approaching the other object is positive, and any velocity receding away from the other object is negative. So if the car were moving away from the person, that's receding away, that's recession, that would be a negative velocity. If the person were running away, that would be a negative velocity. If the car were moving toward and the person were running away, the car would have a positive velocity for the source velocity. The person would have a negative velocity for the observer velocity.